The so yeah, the first group of binders and the exams, I think I can have back by Wednesday. That's what I'm trying to do. Um, so I don't have anything else to say about that, I guess. All right, so back to circular motion. And circular motion is a part of particle kinematics. I'm sort of separating it into its own section, but that's that's what we're still doing. You got this member, this bar that's rotating. It has a length of 0.5 meters. And let's say that it's rotating this way with an angular velocity of 10 radians per second. And it has an angular acceleration this way of 20 radians per second squared. And we want to calculate the acceleration of the point P right here. Okay, so let's first think about it the way we think about the motion of particles like in lab. Um, so if this point P is on, well, so why is this circular motion, first of all? Any rigid body, all of the points on that rigid body rotate around in a circle around the point that it's, its point of rotation. So if we were looking at this point, it would be following a circular path like that. This point right next to it would be following a circular path like an inch away from that hinge. And this point is in a bigger circular motion. And this is kind of, yeah, an interesting thing about the difference between angular motion and translational motion. Every one of these points would have a different velocity and a different acceleration at a single instant. But the rigid body is represented by those angular quantities. So every point on here has that same angular velocity and that same angular acceleration. But when we calculate the translational quantities that are associated with that, those are going to be different for each one of those points. And if we calculated them for the point right at the hinge, the velocity and acceleration at that point would both be zero. That's not moving at all. Okay, so let's think about this the way we think about it in lab. So here's the path that the particle moves through. It's part of a circle. And the thing's going this way. So at that instant, the velocity vector is like this, tangent to the path. It's speeding up, so the parallel part of the acceleration is this way. And the perpendicular part of the acceleration path is all this side of the velocity vector, so it's that way. In circular motion, it's always straight toward the center. Oh, and calling it parallel and perpendicular, but in circular motion, this is the tangential acceleration. This is the centripetal acceleration. And the total acceleration is the sum of those two parts of the acceleration. So it's going to be somewhere in there. Okay, so it's going to be somewhere, when we calculate numerically the total acceleration of this particle, it has to be somewhere between those two directions. It's going to have a positive component in the x direction and a positive component in the y direction. That has to be the case, or we thought about something wrong. Okay. Okay, so the tangential acceleration magnitude is angular velocity. No, it's not. Angular acceleration times the radius. And that radius r. One thing to notice about that is, like, if we were looking at the point at the midpoint here, okay, and this thing was rotating that way, r is the distance from the center of the circular motion to the point. So even if this body would still have a length of 0.5 meters, but if we were looking at this point, that r value would be 0.25. Okay. But in this case, we're looking all the way at the end, so that r is 0.5. And so we have 20 times 0.5, so 10 meters per second squared. And we already figured out that that's in the positive x direction. So we kind of, yep, that's right. So the tangential acceleration is 10, 0. The centripetal acceleration magnitude is omega squared times that distance r. Omega is 10, so 10 squared times 0.5, and so that's 50. We already figured out that the direction of the centripetal acceleration is in the positive y direction. So the centripetal acceleration is 0.50. And so the total acceleration is 10, 0 plus 0.50. So 1050. And if you draw that up here, that looks something like this. So right in that range of values that we said it had to be. Anybody have any questions about that?
Centripetal is omega squared times r, right?
Omega squared times r is acentripetal.
Like
Omega times r is the velocity magnitude, the speed. The centripetal acceleration is omega squared r. So now let's talk about one of the things that we use circular motion for a lot is rolling objects. So let's talk about rolling without slipping. Okay, so we're going to use two facts about this. The first one is, and these both relate to the center of the wheel or the thing that's rolling. The center of the rolling object. first one has to do with the speed. The speed of the center, c for center, is equal to omega r. You've seen that formula before. That's the same formula that we use to calculate the speed of a point in circular motion, right? This is a little different, but if you assume that somehow those two things are related, since they're the same formula, it's true. I'm not going through the derivation of how you know that the speed of the center of a wheel or a ball or whatever is that, but the derivation uses the fact that when you calculate the speed of a point going in circular motion, you use that formula. But just recognize that this is talking about a different thing, okay? This is talking about the center, and everything else, when we use this formula for circular motion, we're talking about the speed of a point, any point besides the center, basically moving around, okay? So make a distinction in your head between, so the formula is the same, but this is different from that formula that we use in circular motion. And then the second fact is the acceleration of the center. And that says that the magnitude of the acceleration of the center is equal to the absolute value of alpha times r. And both of these parallel to the surface, along the surface that the thing's rolling on. So in rolling, and rolling without slipping is basically, that's just a way of saying rolling. If the thing's sliding along, then we need to know more about it to calculate anything. But in rolling without slipping, if you want to find out the velocity or the acceleration of any point that's not the center, you want to find the velocity or the acceleration vector of a point that's not the center, then use the rules, those two facts above to find VC or AC. And notice that when we talk about the velocity of C and the acceleration of C, we're talking about that relative to the ground. And then use relative motion to find the velocity or acceleration of the other point. So to find velocity or acceleration of another point. Okay, so I'll show you how this works. And the relative motion equations would then look like this. The velocity of the point on the wheel or whatever relative to the ground is equal to the velocity of the point on the wheel relative to the center plus the velocity of the center relative to the ground. Okay, so this is what we calculate using the rules of rolling without slipping. This, so now think of what we're talking about here. We're talking about calculating the velocity of a point on a wheel as if acting as if the center of the wheel is fixed. That's what relative to means. And so this is just circular motion. We're assuming that the center of the wheel is stuck there, even though it isn't, and we're calculating the motion of that other point around it. So this is circular motion. And same thing with the acceleration. So the acceleration of the point relative to the ground is equal to the acceleration of the point relative to the center plus the acceleration of the center relative to the ground. So again, this one just comes from rolling without slipping. This one's circular motion. And you can go from there. Let's see. So let's calculate. Anybody have any questions about that? Yeah. P, C, and G. Okay, so P is the point of interest on the rolling object. C is the center of the rolling object. And G is the ground. Okay, so let's calculate so let's just imagine a wheel rolling along. It's supposed to be roundish. So let's say it's rolling this way. So it's going to be moving this way. And let's say that the angular velocity is, well, let's do it first with numbers and then, we can see it in general later. So let's say that it's moving this way with an angular velocity of 5 radians per second. And let's say that it's slowing down with a angular acceleration of 2 radians per second squared. And let's say the radius is 0.5 meters. So first, let's figure out the velocity of the center. And while we're at it, let's figure out the acceleration of the center. Then let's calculate two more velocities. So let's calculate, I'm going to call the point that's in contact with the surface A, and the point at the top B. So let's calculate the velocity of the point A and the velocity of the point B. And then as the last one, let's calculate the acceleration of the point A. So if I'm using the usual coordinate system, for part A, the velocity of the point C is going to have a magnitude of omega times r, absolute value. Omega was given as 5 radians per second, and r is given as 0.5. And so the speed of the center is 2.5 meters per second. And now we have to figure out the direction. So if it's rolling, it's rotating clockwise, which direction is this wheel going to be rolling? Well, I guess I already drew the arrow there. Yep, it's going to be rolling in the positive x direction. And so that velocity vector is positive 2.50 meters per second. And then the acceleration of the center, the magnitude is the absolute value of alpha times r. So that's 2 times 0.5, so 1 meter per second squared. And now we have to think about the direction of that acceleration of the center. Okay, what do we know? How can we figure out the direction of the acceleration? Well, we know that the angular velocity and angular acceleration have opposite signs. Okay, that means the rotation is slowing down. If the rotation is slowing down, is the speed of the center, is the center speeding up or slowing down? Slowing down, yep. And so the acceleration of the center has to be in the opposite direction of the velocity. Anybody have any questions about that? For the velocity? Because you just have to, I drew this arrow here saying it's moving that way, but in general, what you just have to think about a rotation in a certain direction always corresponds to moving in one direction. So you're just trying to figure out the direction of the motion. If it's going clockwise like that, it has to be rolling that way.
Okay, if it's counterclockwise, it's going the other direction.
Yes. Oh, yep. It's slowing down, and that means if the velocity is this way, the acceleration has to be this way. So the acceleration of the center, and we know that it has to be parallel to the surface, it always is in the negative x direction, 1 meter per second squared, so negative 1, 0. Now we're going to use that information, what we know about the center, to figure out some stuff about the motion of other points on this wheel. And you're always going to have to do that. So anytime you're doing a rolling without slipping problem, you might as well first just calculate the velocity and acceleration of the center. You're going to have to use it no matter what it's asking for. Okay. All right, so we're looking at velocity first of the point A. And the velocity of A relative to the ground, which is what we're trying to find, is equal to the velocity of A relative to the center plus the velocity of the center relative to the ground. The velocity of the center relative to the ground we just calculated. That was 2.50. So now let's think about, so now we got to calculate this. And so to do that, we're going to think about this point A in circular motion around the center, and we're just going to assume that that center is fixed. Okay. And this is rolling clockwise. And so if we're assuming that the center is fixed, what direction would the velocity be of the point A? It's moving clockwise, and so yeah, it's going to be pointing that direction, right? If we fix our frame of reference to this, that point A is moving this way. It's just like all the circular motion problems we did before. So, so we have the velocity that way. And the magnitude of the velocity right before, like I think. So the speed of that point A is equal to omega r absolute value. And I want you to notice that now this isn't rolling without slipping that we're doing, without slipping. It's going back to the circular motion equations that we've been using like last class. It seems like maybe an unnecessary distinction in a way, but it's sort of key to understanding the thought process here. And those numbers are the same, so that speed is equal to 5 times 0.5. And so you get 2.5. It's in the negative x direction, so the velocity of that point A relative to the center is negative 2.50. Any questions about that? The direction? Yeah. Yes, numerically. Exactly. That's right. So now we're not thinking, like the key thing is now on this step, we're not thinking about a wheel that's rolling anymore. We're thinking about this being fixed and this thing, every other point moving around it with the angular velocity and angular acceleration that we had, that we were given in the problem. Okay. So now we can put it all together. The velocity of the point A relative to the ground is equal to the velocity of the point A relative to the center plus the velocity of the center relative to the ground. So that's equal to negative 2.50 plus what was the velocity of the center relative to the ground? Positive 2.50. So the velocity of A relative to the ground is 0. Okay. So in other words, at each instant, the point on a rolling object that's in contact with the ground is at rest. It has 0 velocity. And that might seem sort of funny at first, but when you think about, like if you had to think about a mathematical definition of something not slipping, a point in contact with the ground, what does it mean for that point not to slip? The definition you'd come up with would probably be something like, well, the ground and that point have to have the same velocity, because if they're moving relative to each other, that's slipping, you know. And so this sort of just has to be the case. So anything that's rolling, at the instant the point is in contact with the ground, it has 0 velocity. At the next instant, 0.001 seconds later, it'll be moved away from the ground, and then it'll have a non-zero velocity, like you know, go back to moving. Anybody have any intuition about what the acceleration will be of that point that's in contact with the ground at every instant? That's pretty, yeah, I mean, you'd think sort of for the same reason, like if the thing isn't slipping, it can't have a different acceleration than the ground. It turns out that it's only the part of the acceleration that's parallel to the surface that has 0 acceleration, you know, because that would be the acceleration that would make that point sort of grind against the surface, you know. It will still have a component of acceleration perpendicular to the surface, because that comes from centripetal acceleration, and that does not affect whether the thing's slipping or not. That's just it coming down to touch the ground and then lifting back up. So that's what we'll see eventually when we get to that part. Okay, so now we're going to calculate part B. Now we want to calculate the velocity of the top point on a wheel or any rolling object. So the velocity of that point B at the top relative to the ground is equal to the velocity of B relative to the center plus the velocity of the center relative to the ground. This is what we calculated before. And this one, again, we're going to do using circular motion. Okay, so we have this thing moving clockwise. If we're assuming that C is fixed and we're just calculating the circular, you know, using circular motion equations to calculate what B is doing around that fixed center, what direction is the velocity vector? To the left or the right? The right. And so the speed of that point B, using the circular motion equations, is omega r. And that, again, is 5 times 0.5. So for the speed, we get the same thing. And that would be the speed of every point on the surface of this wheel. This time it's in the positive x direction. So the velocity of B relative to the center is 2.50. And now we'll put this into the circular motion equations, the relative motion equations. So the velocity of the point B relative to the ground is equal to the velocity of B relative to the center plus the velocity of the center relative to the ground. And so that's 2.50 plus 2.50, so 50. And generally speaking, we're always going to see this. The point at the top of a rolling object, and when I say top, I actually mean farthest from the surface. So this all works on an incline too, and then the top wouldn't exactly be the highest point. It would be, you know what I mean, perpendicular to the surface. The point at the top of a rolling object always goes twice as fast as the center. So if you're riding your bike at 10 miles an hour, the top of each wheel at every instant is going 20 miles an hour in the same direction that you're going. Okay, that was D. And then the last one, now let's calculate the acceleration of that point A. Okay, so E, we're trying to calculate the acceleration of the point A relative to the ground. And again, you know, I mentioned this before. You might think no slipping means the acceleration of A is equal to the zero vector. Really, it just means that the part just the part or the component of acceleration that's parallel to the surface is zero. So we'll see that. We're going to see that the acceleration of that point A has no part parallel to the surface. In this case, that means it's not going to have any x component, but it will have a y component, and that's generally true. So we know that the acceleration of A relative to the ground is equal to the acceleration of A relative to the center, plus the acceleration of the center relative to the ground. The acceleration of the center relative to the ground we calculated before. That was -1, yep. negative 1, 0. This one we're going to have to calculate. So here's the center. It's going clockwise. And so now we're going to have to think for this point A, let's think through all the directions. And, you know, it's just like the kind of circular motion problem that we did right before this. There is a velocity this direction.
It's going to go counterclockwise, no?
The which one?
The radius per second squared. I was going to go.
In this case, so if you were told that, yeah, the 2 radians per second squared, right, it does go counterclockwise. Yeah. But we're going to think through this right from the start, like a circular motion problem where we have to figure out the direction of the velocity, use that to figure out the direction of the tangential acceleration, and then do the centripetal acceleration. So the first thing, to figure out the direction of the velocity, we need to use the direction of the angular velocity. And that one is clockwise. Okay. Okay, so the velocity is going this way. It's slowing down, so the tangential acceleration is going this way. Centripetal always points toward the center. And now we're going to figure out the magnitudes of these 2 parts of the acceleration. So the magnitude of the tangential acceleration is alpha r, and that is 2 times 0.5, so 1 meter per second squared. And then it's in the direction of positive x, the way I have it drawn here. So the tangential acceleration vector is 1, 0. The magnitude of the centripetal acceleration is omega squared r. So that's omega squared. Omega is 5, right? So omega squared times the radius. So 12.5 meters per second squared. And from our picture, that's in the positive y direction. So the centripetal acceleration is 0, 12.5. And so the total acceleration of that point A relative to the center is the sum of these 2 things, 1, 0 and 0, 12.5. So 1, 12.5. And now put that back into the relative motion equation. So the acceleration of A relative to the ground is equal to the acceleration of A relative to the center plus the acceleration of the center relative to the ground. And that is 1, 12.5 plus negative 1, 0. And so we get an acceleration of that point A that's equal to 0 for x, 12.5 for y. And so that 0 comes out the way we expect because there's no slipping. That doesn't mean the acceleration is 0. There's also that centripetal part of the acceleration toward the center of the circle. Any questions about that? Okay, let me say one more quick thing, 1 minute. So what if the surface is horizontal? Well, the easiest way to do that, if you have an inclined surface like this and an object rolling down, is just use a rotated coordinate system the same way you do with like sliding friction problems, where the y-axis points straight out of the surface, the x-axis is along the surface. Then you can do all the calculations exactly the same. Once we get into kinetics, which is the next thing we'll talk about, we'll start that next class. We'll see that the weight force, oh, you haven't done, sorry, I get confused about the class. Oh, yeah, we'll use a coordinate system like this, and maybe I'll do an example like that so you can see how that works. But then it's easy because you still just have the velocity acceleration of the center of this wheel moving parallel to the surface, which is in the x direction. And the centripetal acceleration is still just in the y direction. It makes the calculations easy. You don't have to. You can just give your final answers in this coordinate system. Yep, that's perfectly fine. But later on, we'll talk about how to switch from, so you can get your answers in this and then convert those answers to the coordinate system you're used to. But for now, yeah, just leave them in that coordinate system. Just be clear to me what coordinate system you're using. Draw it on there somewhere. Okay, that's it. See you tomorrow. If you want to turn in your binders today, feel free. If you want to hold on to them, that's fine too.